Alright, this video is on specific heat capacity lab. It's just a pre-lab to kind of get you guys an idea of what you're doing when you come in tomorrow. There is a handout that is on the Chem Assignments webpage. It says specific heat capacity lab paper. So go ahead and click on that and download it, bring it. If not, you can probably just take notes on a separate sheet of paper right here. And then I'll also give you the data table that you need to bring in today or for class tomorrow. So first thing, specific heat capacity, like we said in class, is the amount of energy it takes in joules, usually, to raise the temperature of 1 gram of a substance 1 degree Celsius. So usually, we'll see delta H equals MC delta T. So this being my mass, right, and my specific heat capacity, and the change in temperature will tell me how many joules of heat was transferred. Right? Now, what you're going to be doing tomorrow is you're going to take, right? You're going to take a known sample of water, okay? A known sample of water at a certain temperature. Let's just go ahead and say 0 degrees Celsius, because I'm pretty much going to have it ice water, right? And then you're going to have a metal cylinder, right? Now that metal cylinder will be of an unknown metal. But what you'll need to do is you'll need to mass that metal. Okay, you can get the mass after the reaction taking place. That's fine. Okay. But what's going to happen is that metal is going to go, which is going to be a warm piece of metal. So make sure you use caution when we use our tongs. Okay. I'm going to drop that warm piece of metal into the ice water at 0 degrees Celsius. Now, the temperature of the metal, you'll know because whatever the incubator says on what's the internal temperature of the incubator will also be the internal temperature or the temperature of your metal cylinder, because I put it in there last night and it's been in there for a couple days. So that temperature regulation should mean that that metal should be the same temperature as the inside of the incubator. So make sure you look at the incubator and find out what temperature it's at, because that will be your initial temperature, so to speak. So don't know what that is off the top of my head, but I'm saying it's probably going to be somewhere around 60 degrees, but you'll need, like I said, you'll need to double check. Okay, so what you'll do is when you put the metal into the water, obviously the water is going to cool down the metal, which means, okay, if I was to change my drawing here, okay, here's my metal cylinder now inside the water. Okay, now the water was at 0 degrees Celsius, the metal was much warmer. So the heat should be transferring from the metal out to the water. Okay? Now, I want to know, the whole point of this lab is to find out the specific heat capacity of this metal cylinder and in turn find out the identity of that metal based on a group of literature values that I give you. Okay? So, I have my heat being transferred out of my metal cylinder into the water, which would cause the water's temperature, right? So here's my little thermometer, right? It'll cause the water temperature to increase, right? So as my water temperature is increasing, the temperature of my cylinder should also be going down. Well, it will reach what we call an equilibrium, a thermal equilibrium, where the temperature of the water and the temperature of the cylinder will be the same. And what you'll look for on the thermometer is when, okay, the temperature is going to go up, 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 and all of a sudden when it stops and just kind of slows down, or it's pretty much at the same temperature for, say, 5 minutes or longer, okay, then that is your thermal equilibrium, and that would be your final temperature, okay? So how this looks is going to be the thermal energy of the metal, okay, is going to be equal to the thermal energy of the water. Okay, now you're thinking, well, that doesn't make sense. Well, it makes perfect sense, okay, because I cannot create or destroy energy. So all the energy, the heat, the thermal energy that was inside the metal was transferred to the water, okay, and all of the thermal energy that the water received came from the metal. Now, usually when we show energy being lost, we usually give delta H a negative sign, okay? So the negative H of the metal is going to be equal to the delta H of the water. Now, please do not confuse this negative sign as some sort of monetary, or not monetary value, but some sort of numerical value on a number line. It doesn't. These positive over here, okay, I'm not even going to put the positive, but I'll put a little just so you can see. Okay, that positive there and that negative that's on the metal side, that's just showing the direction of the energy. It is not saying that it's negative energy. Okay? It's just telling me the direction of that energy, which means if the delta H of the metal is negative, that means the metal is losing energy. And if the delta H of the water is positive, that means it's gaining the energy. Okay? Well, you should know that delta H is equal to MC, oops, make that a big C, C delta T, right? And that's the case over here as well. Let's get rid of that line, all of it. And I should know that this is equal to M times C times delta T. Well, if the amount of energy that's from the metal is equal to the amount of energy that's absorbed by the water, then what I do is I set them equal to each other. Okay, so this is the kind of stuff you're going to need for this lab, so keep this in mind. You're going to need to know the mass of the metal. Okay, you're going to need to know the mass of the water. Right? The temperature change of the metal and the temperature change of the water. This is all going to be in your data table. Okay? Now, luckily for you, you already know what the specific heat capacity of water is. So you can calculate delta H already. You know the heat transfer that the metal lost. Your job is to use this information to solve for the specific heat capacity of the metal. Okay? And when you use that, you're going to compare it with some literature values, which I'll go ahead and put on the board now. Okay, we have 3 elements and 3 alloys. So we have aluminum, which is 0.90 joules per gram degree Celsius. Iron, which is 0.45 joules per gram degree Celsius. We have copper at 0.40 joules per gram degree Celsius. Let's see, steel at 0.50 joules per gram degree Celsius. Let's see, brass 0.35 joules per gram degree Celsius. And lastly, bronze at 0.30 joules per gram degree Celsius. So what you'll be doing is you're going to solve, right? We're going to have, MC delta T. This is the metal side. And then MC delta T, that's the water side. You're going to be solving for this specific heat capacity right there. And whichever one is closest to these literature values is the identity of that metal. Okay, and I will let you know what the identities of the metals are after the fact, so when you guys do your abstract or do your lab report, you'll know what metal you actually did have. Okay, so make sure you have these literature values written down. If you have any questions about the lab overall, make sure you send me an email. Your data table that you need to copy down is going to be the last slide that I pop up right here. Once you have that written down, you can come to class prepared. Make sure we bring closed-toed shoes. Also, if you want to, like I said, you can go to the table of contents. There's going to be a little link that'll say Specific Heat Capacity Lab. You can click on that, and it'll bring up all these literature values as well as this data table right here. Right? So, if you don't have a printer, you can't print it out, make sure you jot this down before you come into class. So this right here, it's kind of hard to see. That says temperature initial of water. This says temperature final of water. This is change in temperature. This is temperature initial in metal. This is temperature final metal. This is temperature change in the metal. This is mass of water, mass of metal, specific heat capacity of the metal, and then the average. You're actually going to do 2 trials. One of them is putting, right, trial one right here is going to be putting hot metal into cold water, and then the second one is once the metal has reached, equilibrium, it's now going to be really, really cold in the cold water, then you're going to put that cold metal into some room temperature water, or maybe even some warm water, I haven't decided yet, and we'll see if there's a, you should end up with two different C values, but they should be close even though you're not really doing the same trial over. Okay?